So I'm going to talk about a study of bandwidth denial of service attacks against Tor. I'm Rob Jansen from NRL, and this is joint work with my colleagues Tavish and Micah from Georgetown University. So in this work, we explore the costs and effects of bandwidth denial of service attacks on Tor. The most exciting contribution is for an attack that costs 3 gigabits per second and costs anywhere from $140 to $1,600, depending on how you count. We can cause Tor downloads to become 47% slower across the entire network. That's all I have. Questions? It's good to see you guys are still awake in this last session of the conference. So anonymous communication separates identification from routing. This is a system that provides unlinkable communication between a client and where they're visiting on the internet. Anonymous communication systems protect user privacy and safety online. Tor is the most popular anonymous communication system with between 2 and 8 million daily active users. It has 6,500 volunteer relays that transfer a total of 200 gigabits per second in aggregate. Because Tor is popular and used by people all around the world, it's been a target of a lot of anonymity attacks. There's been attacks, website fingerprinting attacks, traffic correlation attacks, and routing attacks that have been published over the years and continue to be important areas of research. But some of these attacks are complicated, and math is hard. And so what I'm interested in this work is looking at more simple denial of service attacks that can also have a dramatic effect on the network. So our focus in this work is denial of service. We're not the first to look at denial of service on Tor. There have been a variety of studies over the years. In 2007, Borisov et al. Presented a selective service refusal attack. And in 2014, Geddes et al. Presented a resource exhaustion attack. These attacks have a goal of causing clients to not be able to access the network. There have been a couple of studies focusing on CPU, computational resource exhaustion attacks. These attacks cause Tor to conduct CPU operations, cryptographic operations, to keep the CPU busy. There was an attack in 2009 called the long paths attack, where you would build an infinite length Tor circuit as a means to consume bandwidth. And in 2014, the sniper attack was presented with the goal of consuming memory resources and causing a relay process to be killed by the operating system. In this work, we focus on bandwidth denial of service attacks using some techniques from previously published work as a way to consume bandwidth on the network. So denial of service attacks are not a hypothetical threat. This is a realistic threat. Denial of service attacks have been reported on the live network. In January 2018, there was a report of an ongoing denial of service attack on Tor. This led the developers to develop a denial of service mitigation subsystem that would help mitigate the effects of such an attack. So this is a real threat. These attacks are relatively easy to carry out, as you'll see, and we need to better understand these attacks so we can help develop better defenses against them. So in this work, we explore 3 research questions. How vulnerable is Tor to denial of service attacks? How costly are these attacks to carry out? And what effect do they have on client performance? In the paper, we look at 3 different components of Tor. We look at bridges, the Tor flow bandwidth scanning infrastructure, which helps produce weights to balance load across the relays. And we look at a relay congestion attack. These attacks have various costs and various effects on performance. Throughout the paper, we did these attacks in a private Tor network. We did not do them on the live Tor network for ethical reasons. We used a high-fidelity simulation using the Shadow simulator. We did some measurements on the Tor network, but they were mostly client measurements, and we didn't store any information about any users. So for the rest of this talk, I'm going to focus on the relay congestion attack and explain how it works, what the costs are, what the effects are. If you're interested in the other attacks, please see the paper for more details. OK, so the way Tor works is when a client wants to visit a destination through the Tor network, it builds what's called a circuit by choosing 3 relays in the network and extending a connection through each of these relays in a telescoping process. Through this process, they create a shared key with each relay so that they can encrypt traffic multiple times and send it through the circuit. The client then instructs the final relay to connect to the internet destination. So in this process, after this process, no single point on the path can learn both the client and the destination. So this provides unlinkable communication to the client. So a relay congestion attack can be launched by extending a circuit from 3 hops up to 8 hops. This is allowed by the Tor protocol. Previous work that explored long paths in Tor caused Tor to reduce the maximum circuit length to 8. But you can still build an 8-hop circuit as of today. So step 1, build an 8-hop circuit. The circuit can be targeted or indiscriminate. Targeted means if you have a specific relay that you're trying to congest, you can repeat that relay up to 3 times in the same circuit. Indiscriminate, you just choose relays following Tor's regular path selection algorithm, which is the approach we take in this attack. So once you have your 8-hop circuit, you simply initiate a GET request for large files from some internet web server, and the web server will send this data. All 8 relays will download and upload as they're forwarding traffic towards the client. Step 3 is the client can stop reading on the TCP connection to the first hop relay, meaning that they no longer call the read function in the kernel, so data won't be transferred from the entry to the client. However, the client can still write on this connection, and this is important because the client will continue to send Tor's flow control cells to the exit node, which will instruct the exit to continue sending data, reading data from the server and sending it towards the client. And this way, the traffic will continue to be sent through the circuit and consumes resources at all of the relays. Step 5, repeat. You can build thousands of these circuits at the same time. Important things to note when you're building these circuits is spreading them out across different relays. You can choose any relay in the network as a first hop into the network. And each attack circuit uses a different socket TCP connection in order to have more control over the attack circuits. So as a result of this, lots of data from internet web servers will be sent into the network. The network will send it between each other 8 different times. And then, because the client is not reading, most of the data will get stuck at the entry points. OK, so we implemented this attack, and we evaluated it in a private Tor network using the Shadow simulator. Shadow allows you to do this in a private network without harming any users. We built a 10% Shadow Tor network, which is about 10% the size and capacity of the live network. We ran thousands of clients and servers in the network to create realistic background traffic. And then we explored the effects of attack. We looked at various attack strengths, so various numbers of attack circuits. And we measured network load, attacker resource usage, and client performance during the attack. So the results are shown here. The graph on the left is attacker throughput. So this is how much bandwidth the attacker is consuming during the attack. And the graph on the right is Tor relay goodput. This is how much bandwidth all of the relays combined in the network are consuming. We're showing 2 different attacks here. The 20K circuit attack is the same attack as the other one, except the client is actually doing the reading thing. The stop reading attack is, as I previously described, where the client stops reading from the entry point. So the first thing to note here is that in the regular attack where you do the reading, the bandwidth amplification factor reached 6.7. So the attacker consumed about 200 megabytes per second on average through the attack and caused an increase of about 1.2 gigabytes per second on the network during the attack. And then in the stop reading case, the attacker used significantly less bandwidth because it's no longer reading this data from the circuits, from the network. It's still sending cells during circuit construction and downloading cells during circuit construction, and then sending these periodic flow control cells, so it does use some amount of bandwidth. Aggregate relay goodput dropped a little bit because some of these circuits are timing out and the client isn't realizing this, so it's causing some loss in efficiency, but we still achieved a bandwidth amplification factor, in this case, of 26, which is quite scary. So in addition to the effect on the attacker and on the Tor network, we looked at the effect on Tor performance. So this graph looks at the download time, time to first byte, and time to last byte across various size files that were downloaded during the experiment in both the no attack 20K circuit and the stop reading attack case. The highlight here is for the 20,000 circuit attack, time to first byte increased by 138%, and time to last byte increased by 120% across all the downloads. And then again, in the stop reading case, this was had a slightly smaller effect. This is also less costly to the attacker because they're not reading, but we achieved a 48% increase in time to first byte and 47% increase in time to last byte across all downloads. Okay, so how much does this attack cost? The attack that we did in Shadow was, as I mentioned, on a 10% Tor network. So we extrapolated this up to a full Tor network by multiplying most of our requirements by 10. So for 200,000 circuits in the live Tor network, our attacker would consume roughly 3 gigabits per second of traffic and would require 20 IP addresses in order to not trigger Tor's denial of service mitigation system that I mentioned earlier. And then how much does the bandwidth cost? For this question, we surveyed, the table on the right, table 2, shows a survey of different providers and how much they charge for dedicated servers with a certain bandwidth quota. And we surveyed some of these providers, and we came up with a mean amortized cost of 70 cents per hour per gigabit per second of traffic. And so we use this amortized cost in addition to assuming that IP addresses cost $5 each to estimate conservatively a cost of $1,647 to conduct this relay congestion attack on the live network. Now, if you want to get a little bit more optimistic, you can say, well, actually, VPSs are much cheaper. You can get a VPS for $7. I used to have one of these. They claim to offer a gigabit per second, although likely they offer far less than that, and the links are probably shared, so you might not be able to achieve that. But even if you bought 20 of these VPSs to get the 20 IP addresses, this is only $140 per month. So optimistically, the cost of the attack is potentially much cheaper than the conservative estimate that we have in the paper. So another question is, well, what if you use this 3 gigabits per second for an anonymity attack on Tor rather than a denial of service attack? So we looked at this. We compared our attacks, or how much you could do with a Sybil attack, where the attacker would use this bandwidth to run relays in the network instead, and then use those relays in a denial of service attack or a de-anonymization attack. So in the denial of service attack, the goal is to get your Sybil relays to appear in as many circuits as possible, and then whenever someone builds a circuit through those relays, you can just drop the circuit or arbitrarily degrade performance on it by slowing traffic down, et cetera. So the question for the attacker is, how can I get my relays to exist in the most relays possible? And to do this, exit relay bandwidth is the scarcest in the network. So the best option for the attacker is to run exit relays. This will give them the highest probability of appearing in a circuit. And with 3 gigabits per second of traffic, you can appear in a roughly 4.5% of circuits and then arbitrarily degrade performance on those circuits. In a de-anonymization attack, the goal is to appear on both ends of the circuit in order to compromise anonymity of the client. So you appear on one end, you know the client. You appear on the other end, you know the server. Previous work has looked at this issue and found for a given bandwidth budget, the best allocation of resources is to a 5-to-1 ratio of guard bandwidth to exit bandwidth. And this is because it's more difficult to become a client's guard node because clients choose a guard and stick with it for several months. So it's more advantageous to put more of your resources towards running guard nodes in that case. So with this allocation, attacker can appear as a guard in circuits 2.8% of the time and as an exit in circuits 0.8% of the time for a compromise rate of 0.02% of all the circuits. So compared to our attacks, our attack works across the entire network on all circuits that are built, whereas these attacks are a little bit more nuanced in how they function. OK, so how do you mitigate the relay congestion attack? The attack relies on three main features. One is the ability to stop reading from circuits. So I have actually co-authored a Tor proposal called authenticated sendmes, which has been implemented in a recent version of Tor. The way authenticated sendmes work is every 50 cells that the exit sends toward the client, at the end of that 50th cell, it adds a nonce to the cell. And then the client needs to read and return the nonce from that 50th cell when it's sending back the flow control cells to the exit. And if the nonce doesn't validate, the exit will drop the circuit. So this essentially stops the stop reading part of the attack and will reduce that bandwidth amplification factor from 26 down to 6.7. Another thing our attack uses is the ability to build 8-hop circuits. Tor only needs 4 hops in the current protocol, and so we could reasonably reduce the circuit length to 4 hops in the current network, and that would further reduce the bandwidth amplification factors that an adversary could achieve. And another issue is that an attacker can use all of the relays in the network as the first hop. And this is actually a challenging problem because Tor is a privacy-preserving network, and relays can't just store information about users and share that information with others. From an anomaly perspective viewpoint on this, it would be easy to detect an attacker who's connecting to all of the relays at the same time because that's not a normal behavior. But in order to share the information across relays in a way that doesn't harm regular users, this is a non-trivial problem. So this is future work, developing a privacy-preserving defense against Sybil attacks, and then using that to detect if attacks are happening in the network, measuring how often they happen, and using that to prevent such attacks. So that's all I have. Again, we looked at 3 attacks: the bridge congestion attack, a bandwidth authority attack, and a relay congestion attack. I only went over the relay congestion attack here, but the others, there's more details in the paper about the other attacks, and I discussed some future work. That's all I have. Thank you for your attention.
OK, we've got a bit of time for some questions and a microphone right here.
Hi, thanks for the presentation. Really cool work. Bobo from Facebook. I had a question. In the cost estimation, you scale by 10x in order to scale your costs. I was wondering if you knew that the characteristics of the network that are relevant for the cost to the attacker do scale linearly like that. I was also wondering about the mitigation of every 50th cell having a nonce. Not sure I followed that. This may just be ignorance on my part, but can the attacker simply read every 50th cell and discard the other 49 and get most of the amplification?
OK, for the 10x linear adjustment, Shadow was designed to match the bandwidth of the Tor network, like to match a distribution of bandwidth in the network. So 10% of the bandwidth in Shadow, if you multiply that by 10, you'll get back to the actual distribution of Tor traffic in the live network. So I think that's an appropriate multiplier. For your second question on the authenticated sendmes, the attacker can't read every 50th cell because it's a TCP stream, and it has to read all of the data in order to get to the 50th cell. You can't do selective reading, so yep.
Hi, Rod. Really good, really cool work. I'm Jerry from UMass Amherst. So in the mitigation method on the previous slides, you mentioned that we can reduce the 8-hop circuit to the max ability to 4 hops. But what I'm wondering is whether the attacker can just run multiple Tor clients and do the Tor over Tor, Tor over Tor, Tor over Tor attack.
Yes.
So multiple Tor clients, just set up the proxy to each other's listening port.
That's a great point. That was one of the attack variants that we had in our paper. I called it the tunneling strategy. You can tunnel Tor connections through other Tor connections. Mm-hmm. Tor could feasibly eliminate this feature by exits not allowing exit back into another relay that's running in Tor. So you could prevent this feature, which is why I didn't focus on it during this talk. But currently, I believe it is possible to do the tunneling strategy.
Gotcha. Thank you.
Yep.
One more, and while that, can the next speaker come up and start setting up?
Hi, Stephen Sheffy from Middle Tennessee. I was wondering, so would reducing the number of hops possibly decrease anonymity? And could that be counteracted by maybe limiting the amount of traffic you can send if you're using a higher number of hops?
Does reducing the number of hops reduce anonymity? So currently, most users build 3-hop circuits. So I'm not suggesting that we reduce it from that. I'm just suggesting what the protocol allows. The protocol will allow you to build 8 hops. But for anonymity reasons, we only really need 3. It's been established in research.
Okay.
And I think you might have asked another question, but I didn't quite hear you. So maybe we could take that offline, because I think I'm out of time.
Okay. Thank you.
Sounds great.
right.
Let's thank Rob again.